Good morning, everyone. Today is February 4th, 2017, and this is the John Chappell Natural Philosophy Society Science Chat. Today we have a special guest. We have, is it Professor Assis? And he's going to be giving us a presentation. The presentation will last about an hour, and then after that, we'll open it up for questions and answers. So I'll let you take it away.
Okay, so in the first place, I wish to thank David Hilster and Franklin Hu for this nice invitation to be here today with all of you. I will be talking about relational mechanics, which is a subject I have been developing for the last 30 years at the University of Campinas in Brazil and abroad. The main topic, I will discuss two experiments, essentially. I will first review classical mechanics, which was developed by Isaac Newton in his book, The Principia. And in this book, he presented the famous second law of motion and his universal law of gravitation, not with formulas like this in words, but nowadays we write this equation, which would be equivalent to Newton's law of gravitation. And the simplest problem of dynamics, which you can think about, is a problem with a constant force and a constant acceleration. So we will be dealing with this problem today. So when we have a free fall in Newtonian mechanics, then we have an apple falling to the ground, to the earth, with a certain acceleration. So we apply Newton's second law of motion, force equal mass times acceleration. The force here is the weight of the apple, mg. So the two masses cancel, and we obtain that the acceleration of free fall will be the small g, which, if we apply Newton's law of gravitation, will be capital G, mass of the earth, divided by the radius of the earth square. When we plug in the numbers, we obtain 9.8 meters per second square. So this is the simplest problem in dynamics, constant force and constant acceleration. And this seems to be a simple two-body problem, as we are in free fall, there is no friction. However, in reality, this is not a two-body problem. There are stars and galaxies around the Earth. Newton didn't know about the galaxies, but anyway, there are stars and galaxies. So in principle, we must take them into account. This is a real problem. This is not a short thinking experiment. This is a real problem. So we might think that the force of each star, as Newton's law of gravitation falls as 1 over r square, the force of one star is negligible, extremely small. The same for one galaxy, because it is too far away. But when we take all the stars into account, all galaxies, the force which they exert on the apple might be huge. If there are infinite number of stars and galaxies, the force exerted by all of them might even go to infinity. So in principle, we cannot neglect them. And Newton, he was so bright that he took them into consideration. What I will present now is the most important theorem which Newton proved in the Principia. This is theorem number 30. This are Newton's words. If to every point of a spherical surface there tend equal centripetal forces decreasing as the square of the distances from these points, Newton, I say that a corpuscle placed within that surface will not be attracted by these forces anyway. So the spherical surface here, we might imagine a set of stars around the earth. So no matter how far, how large is the distance of these stars, there are stars in all directions. And so the force which they apply on the apple, they just cancel. So the force goes to zero, not only in the center of the shell, where it would go to zero by symmetry, but everywhere inside the shell. But this theorem, which Newton proved in the Principia, is only valid for forces which fall as 1 over r square. If the force of gravitation were, for instance, 1 of r cube or other power laws, the theorem would not be valid. So it's not trivial. It is essential. It is this theorem which allows us to forget about the influence of the stars and the galaxies on the apple. Only due to this theorem, not because they are far away, because, for instance, I believe there are infinite many stars and galaxies in the universe. So the force which all of them exert on the apple, in principle, should not be forgotten. And Newton did not forget them. Okay, so with this theorem, we can forget the influence of the stars and galaxies. But now the Earth is huge. Different parts of the Earth attract the apple with different forces because they are at different distances from the apple. So the next theorem, Newton considered a body outside the spherical shell. Here are his words. The same things supposed as above, I say that a corpuscle placed without the spherical surface is attracted towards the center of the sphere with a force inversely proportional to the square of its distance from that center. So we recover Newton's law of gravitation, but now with the distance between the apple and the center of the Earth, supposing the Earth essentially spherical. Okay, so now we can go back to free fall in Newtonian mechanics. So this Newton's second law, the force of the Earth plus the force of the stars acting on the apple is equal to the mass of the apple times its acceleration. By Newton's theorem 30, the force of stars and galaxies goes to zero. And then we can divide both sides of this equation by the inertial mass of the apple, and then we obtain that the acceleration will be a ratio between the gravitational and inertial mass of the apple times capital G mass of the Earth by radius square. This is what comes from Newtonian mechanics. Only this. In principle, from Newtonian mechanics, an apple might fall to the ground with a different acceleration from a coin or a feather or any other substances. But then comes a very important experiment performed by Galileo. He showed that in free fall, when we can neglect the influence of air resistance, all bodies fall together to the ground with the same acceleration. For instance, with pendulums, one of a cork and another with lead, he showed that both pendulums would oscillate with the same frequency if both pendulums have the same length. So it is this experiment of Galileo which allows us to cancel the gravitational mass of the apple with the inertial mass of the apple. Because according from Galileo's experiment, this ratio is the same for all bodies. For instance, but this is not trivial, not at all. For instance, here in my hand, I have a cork and a metallic coin. So they have the coin is heavy, the cork is light. They have different size, they have different shapes, and mainly they have different chemical constitutions. One is organic, the other is metal. So everything is different. There is in principle no reason why they should fall to the ground with the same acceleration. This is not at all trivial. It's a mystery because everything is different. So they should fall to the ground with different accelerations. That would be natural. But this is not what happens. So this experiment by Galileo indicates, according to Newtonian mechanics, that somehow gravitation is connected to inertia. To show that this is not trivial, I present in this slide 7, at the left, two bodies falling in the same gravitational field, 1 and 2. No matter their weights, shapes, or chemical constitutions, they fall with the same acceleration in the same gravitational field. At the right, we have a proton and an alpha particle being accelerated inside a capacitor. The electric field is the same for both, acting the same way in the proton and in the alpha. But they move with different accelerations. Why? We say, well, because the alpha has twice the charge of the proton, but has 4 times its mass, because it has also 2 neutrons. So the acceleration of the alpha particle is half as large as the acceleration of the proton. So these two examples show that inertia is connected to gravitation, but not with electromagnetism. Newton in the Principia discussed that inertia is not connected with magnetism, because I can a piece of iron I can magnetize without changing its weight or its amount of matter. Okay, but this is not trivial. So this is very deep result. So have we solved everything in the two-body problems? Not yet. Why not? So we go back to the free fall of the apple. This acceleration of 9.8 meters per second square is the acceleration of the apple relative to what? Well, we might say it's obvious. It is the acceleration of the apple relative to the ground where we are performing the experiment. But Newton said no. In his laws of motion, in his own words, we should utilize the frame of reference of absolute space. In his words in the Principia, he said, absolute space without relation to anything external remains always similar and immovable. So it's not acceleration of the apple relative to the ground. Why not? Well, Newton utilized the same second law of motion to study, for instance, the orbit of the Earth around the sun. The Earth is not moving relative to itself. So when you apply F equals ma to study the orbit of the Earth, you need another frame. It cannot be the Earth. So we might think, oh, the sun or the fixed stars. But in the Principia, Newton said, maybe there are not a single body who is really at rest. Nowadays, we know that the solar system moves around the center of our galaxy. So the sun is also not at rest. It moves relative to the background of distant galaxies. So To Newton, it was acceleration relative to empty free space, to the vacuum. The 9.8 is not the acceleration of the apple relative to the ground. But then comes a problem. We don't see empty space. We don't see the vacuum. So how can I measure or know the acceleration of the apple relative to nothing, to empty space? Then Newton made the most important experiment of his dynamics, which is his bucket experiment. Let me just first show what Newton. So this is the experiment made by Newton. At the left, in slide 9, we have a bucket partially filled with water. When the bucket and the water are at rest relative to the ground, the surface of the water is flat. At the right-hand side, Newton did spin the bucket, and then after a while, the water was spinning together with the bucket relative to the ground, and the water rises towards the sides of the bucket. It acquires a parabolic shape. So the equation z equals omega squared r squared over 2g is the equation of a parabola. This is the equation which comes out of classical Newtonian mechanics. So the experiment is very simple. The question is to understand what is this angular velocity. It is rotation of the water relative to what? So according to Newton, the concavity of the water depends on this omega, this angular rotation of the water relative to absolute space, that is relative to empty free space or relative to vacuum. It's not the rotation of the water relative to the bucket, to the airs, nor to the stars. Before continuing, I will make the experiment here for you to see. It's very simple. You can do it at home. Here I have a plastic bottle, transparent so that we can see inside. Newton had a bucket. I have a plastic bottle. And the cross section is cylindrical, okay? Newton had water. I have Brazilian coffee. I recommend to you. It's very nice. So I will perform the experiment so that you can see it. So when the water is at rest, the surface is flat. Then I turn the rope, I turn it, and then I just make it spin very fast in the opposite direction. As you can see, the parabolic shape here. If I stop it, it returns to the flat. Now I spin in the opposite direction. It also acquires this parabolic shape. So the experiment is so simple, and there is no vacuum here, okay? There is air inside my bottle. And so how could Newton prove the existence of vacuum with an experiment made in open air? His bucket was open air. So let us try to understand Newton's reasoning. This experiment is so important that Newton placed this experiment in the beginning of the Principia, before his 3 laws of motion, before his law of universal gravitation. It is the basis of his whole mechanics. So why don't we say that it is rotation of the bucket of the water relative to the bucket itself? Well, let us see the picture here. At left, the water and the bucket are at rest relative to the ground. At the right side, both rotate together relative to the ground. So there is no relative motion between the water and the bucket in both situations. In the beginning, there is relative rotation because only the water spins. But then Newton said, after a while, the water will spin together with the bucket, performing a revolution in the same time. So I'm considering this situation when both rotate together. So there is no relative motion. So no matter what is the force which the bucket exerts on the water in the left side, it will be the same in the right hand side because there is no relative motion between the water and the bucket. So the first material suspect has been eliminated. But then we might say, oh, okay, it's not the bucket, but it is rotation of the water relative to the ground, because at the left side the water is at rest, and at the right side the water is spinning relative to the ground. But Newton said it's not the ground as well. Consider, for instance, this coin which is in my hand. The force which the earth applies on the coin is the weight downwards. When the water is spinning relative to the ground, the weight only points downwards. It does not exert any lateral side because Newton's law of gravitation that does not depend on velocity nor acceleration. So even when the water is spinning relative to the ground, the earth only pulls downwards towards the center of the earth. So Newton could eliminate the influence of the earth as well. And what about the stars and galaxies? Well, by Newton's theorem 30, all of them, they exert no force in a molecule of water when the water is at rest. And it will also not exert any force on the water when the water is spinning relative to the ground, because his law of gravitation does not depend on velocity and acceleration. So with this very simple experiment, Newton was so bright that he could prove the existence of the vacuum, that when something is accelerated relative to the vacuum, there will be a visible effect, like the deformation of water here. So in free fall, that 9.8 meters per second square is not the acceleration of the apple relative to the ground, but the acceleration of the apple relative to Newton's absolute space. Okay? So this was the idea of Newton. But then 200 years later came the physicist and philosopher Ernest Mach, Austrian, and he criticized heavily the Newtonian mechanics. He said there is no meaning in a motion relative to empty space. No effect can appear when something moves relative to empty space. Empty space cannot exert a force, cannot produce an effect. So what was the explanation given by Ernest Mach? In his book, The Science of Mechanics, which came out 200 years after Newton's Principia, he said, the principles of mechanics can be so conceived that even for relative rotations, centrifugal forces arise. Another sentence by Ernest Mach. Try to fix Newton's bucket and rotate the heaven of fixed stars, and then prove the absence of centrifugal forces. So this last sentence is a Gedanken experiment, a thought experiment. But it is very clear with this Gedanken experiment, we can distinguish Newton and Mach. I will show it in the next slide. So it is a thinking experiment. But let's see what we could expect according to Newtonian mechanics and according to the ideas of Ernest Mach. So what would be the shape of the water if it were possible to let the bucket at rest on a table, while the distant stars and galaxies rotated together once a second around the axis of the bucket? So now I will let the bucket here, okay, at rest. And only the stars and galaxies will rotate around, only the stars and galaxies will rotate around the axis of the bucket. What will happen to the water inside? No one knows. We will never know, because this is a Gedanken experiment. We cannot perform it. But we can distinguish theoretically what would happen according to Newton and to Ernest Mach. According to Newton, his theorem 30, the stars and galaxies exert no force inside, even when they are spinning, because his law of gravitation does not depend on velocity and acceleration. So nothing will happen in the water. It will remain flat. If, on the other hand, Mach is correct, and if we could perform this experiment, the water would go up. How much? Depends on the angular rotation between the fixed stars and galaxies and the water. If in the Newton's original experiment he did spin the bucket once a second and the water went up to the border, to the rim of the bucket, then if we let the bucket at rest and rotate the stars in the opposite direction also once a second, then the water should go up to the rim of the border, like in the bottom figure at the right side of the slide 11. But we cannot perform the experiment, and we don't know who is right, who is wrong. I agree with Ernest Mach, not with Newton. Another person who originally agreed with Ernest Mach was Einstein. He created his general theory of relativity in order to implement Mach's idea. Mach did not perform the experiment, we cannot, and he did not show mathematically how the water would be concave, parabolic in this situation. And Einstein had an idea. He did need to modify Newton's law of gravitation in order to show a real centrifugal force. Here are the words of Einstein in his book, The Meaning of Relativity. What is to be expected along the line of Mach's thought? A rotating hollow body must generate inside of itself a Coriolis field and a radial centrifugal field as well. This was what he expected. However, in his general theory of relativity, Thiering obtained in 1921 a force exerted by a spinning shell. And he showed that there is really a Coriolis and a centrifugal force. However, in general relativity, there is also an axial force pointing along the axis of the bucket. Okay, if you rotate the stars and galaxies around the axis, there will be also a axial force, and this will create this strange shape in the water. Okay, the details you can see later on. So now that you have at least understood the main problems of free fall, I will now, in the second half of my talk, speak about relational mechanics, which I have been developing in the last 30 years. So if you wish to see more details, I have a book published in 2014, Relational Mechanics and the Implementation of Mach's Principle with Weber's Gravitational Force. It is available in PDF freely in my homepage. Okay, you can download it and read it later on if you wish. So, relational mechanics is a different theory which implements Mach's principle. It's not Newtonian theory, and it's not Einstein's theory of relativity. It is a different theory. What is it all about? It is based on two postulates. One, the sum of all forces acting on anybody is always zero in all frames of reference. Second postulate, instead of Newton's law of gravitation, we postulate Weber's law for gravitation, which is the Newtonian law, which falls as 1 over r squared, but it has also a velocity-dependent component, r dot square, and an acceleration dependent component, r2 dots. Okay? And we say, for instance, that the sum of forces will be zero in all frames of reference. For instance, suppose Newton's apple. When it is at rest relative to the earth, the sum of force is zero. When we release the apple and it's falling, we will also say that the sum of force acting on the apple is zero. If there is a worm inside the apple, I have an apple here. If there is a worm inside, when it is falling, the worm will also say that the sum of force acting on the apple will be zero, even during the fall. Everyone, always, for all bodies, no matter their motions. But where does this Weber's force comes from? It's not an invention of mine. This was developed by a German scientist, Wilhelm Weber, who worked together with Gauss at Göttingen University. He was a contemporary of Maxwell. He lived at the same period as Maxwell. And 20 years before Maxwell developed his equations, Weber also unified Coulomb, Ampere, and Faraday, but not with field concepts. He knew Coulombs law, which is analogous to Newton's law of gravitation. He knew the law of Ampere, that two currents in the same direction attract and in the opposite direction repel. Ampere obtained in 1822 a force which is similar to Newton's law of gravitation, I1, I2 over r squared. It's a central force, but it also depends on the angle between the two current elements and the angle between each current element and the straight line connecting them, alpha, beta, and gamma. I will not go into details here. And Weber also knew Faraday's law of induction, that if you change the current in the primary circuit, you induce a current in the secondary circuit. So what was Weber's idea? No one knew what a current was. So Weber's idea was simply that current is charge in motion. So if I want to unify these two laws, so Ampere's law, I1, I2, should be essentially V1, V2. But there is no velocity in Coulomb. So Weber said, well, I need to introduce a term proportional to V1, V2, so that I could deduce Ampere's law. If current is charge in motion, then Faraday's law of induction says that when you change the current in the primary circuit, you induce a current in the secondary. So microscopically, if current is charge in motion, when you change the current, you mean that you are accelerating the charge in the primary circuit. So the force in the secondary circuit should depend on this relative acceleration. This was the origin for the third term in Weber's law. So this was his main idea, 20 years before Maxwell. So this is his final expression in the international system of units. So it is Coulomb's law, a term with relative velocity, this r dot, dr by dt, relative velocity between the two interacting charges. And the third term, which falls as 1 over r and has a r2 dots, relative acceleration. And there appears a constant which was introduced in physics here. In the international system of units, we write it as 1 over square root of mu naught epsilon naught. The first to measure this constant was Weber himself, 10 years later, in 1855-56, and he obtained light velocity. So it was the first connection between electromagnetism and light, before Maxwell. So what attracted me to work with Weber's law when I found it in history of science textbooks? The properties of Weber's law are, in the static situation, when dr by dt and relative acceleration go to zero, we recover the laws of Coulomb and Gauss. So the electrostatics is there. It complies with action and reaction. This means that it complies with conservation of linear momentum. Moreover, Weber's force acts along the straight line connecting the two particles which are interacting with one another. Therefore, we have also conservation of angular momentum. And people began to criticize Weber at that time, believing that it was against conservation of energy. But then Weber showed that his force could be deduced from a velocity-dependent potential energy. And he showed that it also complies with conservation of energy. Kinetic plus potential energy is conserved in any system of charges interacting according to Weber's law. Moreover, Weber showed that Ampere's circuital law can be derived from his force law. Also, Faraday's law of induction can be derived from Weber's electrodynamics. For those of you who wish, you can see a proof of all these facts in the last chapter of Maxwell's A Treatise on Electricity and Magnetism. It was wholly devoted to Weber's electrodynamics. I will not go into the details here. But what attracted myself, André, to work with Weber's law was the last property, which I will read now. Weber's force is completely relational. What I mean by that? It depends only on r, the distance between the two charges, relative velocity, dr by dt, and relative acceleration, twice the derivative of r by t. Therefore, it has the same value for all observers and in all frames of reference. It depends only on intrinsic magnitudes of the system, that is, on the relations between the interacting bodies. The observer does not appear here. The frame of reference does not appear here. Only the relative distance, relative velocity, and relative acceleration between the interacting particles. Okay? So, when I discovered Weber's law, I thought, if it's so powerful, why not apply it to gravitation? So now I will leave electromagnetism for a moment and go back to free fall and gravitation. So what is the main... just a moment. For those of you who wish, we have a book that we did publish 20 years ago about Weber's electrodynamics by Kluver. Nowadays, it is published by Springer, who bought Kluver some years ago. So you can see the details in this book, mathematical details, etc. But so what is the main calculation of relational mechanics? So here I present once again Weber's law, which is Newton's law plus a velocity term and an acceleration term. And I will calculate the force exerted by a stationary spherical shell acting on a test particle which is accelerated inside the shell. Okay, I have the shell, and for instance, I accelerate it with my hand. Okay, will the shell exert a force on the internal particle? Remember that according to Newton, his theorem 30, the force goes to zero. But this goes to zero only for force which falls as 1 over r squared. This is the first component of Weber's law. But Weber's has a second and a third component. When you integrate that, then the force no longer goes to zero. The final result is that the force exerted by the shell on the internal particle is minus a constant times the gravitational mass of the test particle times the acceleration of the test particle relative to the shell, not relative to an observer or to a frame of reference. It is relative acceleration between the test particle and the shell. And the mass which appears here is gravitational mass because this force comes from a gravitational interaction. The dimensionless constant lowercase phi, this Greek letter phi, depends on the mass of the shell, on the size, radius of the shell, and on the light velocity. This term comes from Newton's law. Okay, now that I have this result, I can go to free fall in relational mechanics. So how can I say that the sum of force is zero on my apple even when it is falling? Well, let us apply the postulate. What are forces acting on the apple? The earth and the stars and galaxies. So force of the earth plus the force of the stars and galaxies equals to zero. The force of the earth will be essentially Newton's law of gravitation. The force exerted by all stars and galaxies will be the previous slide, which I calculate for a spherical shell, but now integrated over the whole universe. Okay? And when you perform this integration, we obtain minus capital phi MA. This capital phi comes from the integration of the previous result. Then I can pass this minus MA to the right-hand side. Then the two gravitational masses now cancel, and we obtain the result of Newton of free fall acceleration. Now the acceleration depends on the gravitational mass of the earth, the distance is square, the mass of the apple does not appear because it has been cancelled, and the constant of proportionality, which appears here, will depend on Hubble's constant and on the mean matter density in the universe, because now we did integrate the previous result over the whole universe. So the Hubble's constant will appear, and also the mean matter density in the universe, which is essentially 1 hydrogen atom per cubic meter. When we plug in the values of the Hubble's constant and the mean density of matter in the universe, we obtain the universal constant of gravitation. But now this capital G is no longer a fundamental constant. It comes deduced from other properties of the universe. So this slide here is the whole relational mechanics is in this slide. So it presents the essence of the whole relational mechanics. We begin with the postulate that the sum of all forces acting on any body is always zero. Then we deduce an expression analogous to Newton's second law of motion. We do not postulate it. That is, we deduce F minus ma equals zero. In this equation, F represents the usual forces acting on the test body: friction, gravitational, electromagnetic, etc. The expression minus ma represents a real gravitational force exerted by the set of distant galaxies acting on the test body, according to Weber's law of gravitation. The mass appearing here in this minus ma is the gravitational mass of the test body. That is, it's not the inertial mass as in Newtonian mechanics. The acceleration appearing here is the acceleration of the test body, the apple, relative to the frame of distant galaxies. That is, it is not the acceleration of the test body relative to absolute space, as in Newtonian mechanics. So the previous slides is the essence. The whole relational mechanics is presented in the previous slides. Later on, if you wish, go back and try to understand the essence of relational mechanics. And I did show the calculation for a stationary spherical shell. What would be the force if the shell were spinning? The force of a spinning shell acting on a body inside. So Weber's gravitational force exerted by a spinning shell acting on a particle moving inside it, when we integrate Weber's law, we obtain this mathematical expression which appears in slide 23, which shows the minus phi ma, the first term of the stationary shell, But then there is a second term, which is centrifugal component, omega times r. And there is a third component, 2v cross omega, which is called Coriolis in classical mechanics. So you see, if when the set of stars and galaxies are spinning around the Earth in any frame, there will be a real centrifugal and a real Coriolis force acting on the test body according to Weber's law. So now I go back to Newton's bucket experiment according to Newton and relational mechanics. So the expression by Newton is presented in the top of slide 24. Z equals omega square r square over 2g. This omega in Newtonian mechanics is omega of the water relative to empty free space. In relational mechanics, we obtain the same similar expression, but now what appears is angular rotation of the water minus angular rotation of the set of stars and galaxies. So according to relational mechanics, the concavity of water depends on its relative angular rotation between the water and the set of distant galaxies. For instance, in Newton's original experiment, like here, when I perform the experiment here, when I spin it once a second, for instance, so we can forget the rotation of the stars and galaxies. That goes to zero compared to once a second. Now, Mach thought experiment. The bucket is at rest, and I rotate the set of stars and galaxies around the bucket. Now we can put in this bottom equation, omega of the water equals to 0, and when we spin this set of stars and galaxies around the axis of the bucket, the same parabolic shape will appear. So we are implementing mathematically the Gedanken experiment by Mach. We cannot perform the experiment, but we are implementing his idea now mathematically. Okay? So this is different from Newtonian mechanics. Can we test Newtonian mechanics? Can we compare it with Einstein's theory of relativity? Yes. And I will show here only two simple experiments, more to clarify the distinction between these two theories, not to perform the laboratory because the order of magnitude is very small, but to see clearly the distinction between general relativity, Newtonian mechanics, and relational mechanics. Okay? So the first experimental test. In free fall, the apple falls with the acceleration of 9.8 meters per second square. So question, what will be the acceleration of free fall when the test body, like the apple, is surrounded by a stationary spherical shell of mass m, stationary relative to the ground? Okay? According to Newton, by his theorem 30, the spherical shell exerts no force on the apple. So the acceleration will remain 9.8. Einstein wanted the acceleration to decrease in order to implement Mach's principle. But in his general theory of relativity, it was shown that a stationary spherical shell exerts no force inside, just like in Newtonian theory. So in general relativity, the acceleration remains 9.8. According to relational mechanics, on the other hand, the acceleration will be a little, very little smaller. How much smaller? Well, it will be 9.8 times 1 minus a constant. This constant is 2 capital G mass of the spherical shell divided by radius c square. When we perform the calculations with a sphere of 1 meter and 1,000 kilograms, for instance, then this dimensionless constant values 10 elevated to minus 24. So we cannot detect that in the laboratory. But philosophically, these three theories give different answers. Okay? If we could, and these experiments we can perform. I cannot rotate the whole set of stars and galaxies around the bucket, but I can put a single glass spherical shell around the bucket and rotate only the glass shell relative to the ground. I can do this experiment. And the prediction is different. The problem is that the concavity, the free fall, excuse me, talking about the free fall. So I can make the free fall of the apple in the open air and then bring it inside this office here, okay, surrounded by walls. So the acceleration of free fall, according to relational mechanics, should be a little smaller than outside. Second experiment. Consider a bucket at rest relative to the ground. We place a spherical shell of mass m around the bucket. What will be the shape of the water when only the shell rotates uniformly around the axis of the bucket? According to Newton, his theorem 30 in the Principia, the spinning shell exerts no force inside, so the water will remain flat. According to Einstein, on the right side of slide 26, there is this force calculated by Tiring, 1921. There will be a centrifugal force, which will create like a parabolic shape. But in Einstein's theory, there is also an axial force along the axis of rotation. So the water will not be parabolic. It will have this strange shape, which I draw here. And according to relational mechanics, the water, even at rest relative to the ground, if I rotate only the glass shell around it, the water will be a little concave, a little parabolic. How much? It will be the parabolic equation times a dimensionless constant k. If, for instance, I have a spherical shell of 1,000 kilograms, 1 meter radius, spinning in the laboratory, 1 radian per second, and I consider a bucket of side 10 centimeters, then this k will be 10 to minus 24. The water will go up only 10 times 10 elevated to minus 27 meters. So it will not go up, not even a single atom. So, but this experiment we can perform. This is the crucial. I cannot rotate the set of stars and galaxies around the axis of the bucket, but I can rotate a real glass shell around the bucket and let the bucket at rest relative to the ground, just like in this picture in my slide 26. So why don't we perform the experiment? Well, people have tried, but the effect is so small that we cannot detect. But here, at least you see clearly the distinction between these three theories. Each one of them gives a different answer. Okay? So, in conclusion, relational mechanics has two postulates. The sum of all forces acting on anybody is always zero in all frames of reference. And instead of Newton's law of gravitation, we apply Weber's law to gravitation. What are the main results that you can see later on in the book if you wish? We deduce Newton's second law of motion. We do not postulate it. F minus ma equals to 0. We deduce the equivalence principle that the inertial and gravitational masses are proportional to one another. We do not postulate this. This is deduced in relational mechanics. Moreover, we show that the centrifugal and Coriolis forces are real forces of gravitational origin exerted by the set of distant galaxies when they are spinning, for instance, around the earth. So relational mechanics presents a quantitative implementation of Mach's principle. So that was the essence which I wanted to present today. So once more, I thank David Houston and Franklin Hu for this kind invitation. And now I am open to answer your questions. Thank you for your attention.
Okay, if you'd like to ask a question, you can unmute yourself and go ahead.
Professor, did you try to apply your equations to inertia? Do you know the paper of Dennis Kiyama in
Yes.
19? You do it. He's
Yes.
using about the same principle.
1953.
I didn't hear you.
Yeah, yes, I know this paper. What's your question?
You do similar results. You get similar results for
Yes,
inertia then.
yes, I do. Yes, but I my results are deduced utilizing Weber's law for gravitation. Sciama's result, he utilized a different force law for gravitation, similar to Lorentz force law in electromagnetism. So he obtained similar results. I compare his results in my book.
Oh yeah, I look. Thank you.
Okay, you're welcome.
Here is Slobodan Nedic speaking.
Okay.
I would catch on this question maybe. I would also may have question maybe later outside of the scope of your presentation, but
Okay, you can send me emails if you
regarding
wish.
the transformation from coordinates and then integrabilities without Christopher symbols and so on. But here, question would be: is Weber's formula for force derived based on the very principle of invariance or contravariance or whatever, that separation, change of separation, and the acceleration of the separation is independent on the coordinate systems?
Yes, it is independent of the coordinate systems. As you can see in
Oh,
slide
actually,
16.
starting from there, he actually derived the formula for the force, right?
Yes, he didn't begin with that. He did begin with Faraday, Coulomb, and Ampere. And in order to unify these three branches, he arrived at this formula, which I present in slide 16. So this is the original Weber's force law. It
Yeah,
is not based on field concepts like Maxwell. It is a
yeah,
different.
okay, but the basic the name relational mechanics, dynamics.
Yes, the origin of the name.
Relevance of the very separation between two bodies, and then involving that separation, change like velocity of that separation change, and the acceleration of that velocity change. So just wonder, what was the first? Was this result of that kind of combination, unification of those three forces, or was something like kind of calculation, something reasonable to expect and to tailor the forces to satisfy such criterion of invariance or maybe contravariance or whatever?
No. When Weber arrived at his force, it was nothing like invariance. He only knew Coulomb, Ampere, and Faraday.
So
And
that invariance came out from it, actually, right?
no, no. When I talk about relational mechanics, it's not invariance in Einstein's meaning. Like in slide 18, what I call relational, I will read again. It is completely relational. That is, it depends only on r, the distance between the two interacting bodies, the r by dt, which is the relative velocity between the two bodies, and d2r by dt square, which is the relative acceleration between the two interacting bodies. Therefore, Weber's force has the same value for all observers and in all frames of reference. It depends only on intrinsic magnitudes of the system, that is, on the relations between the interacting bodies.
Okay,
This
then.
is
Okay.
what I call relational, because, for instance, when we have in classical electromagnetism, the opposite of Weber is Lorentz force law, QE plus QV cross B, charge times the electric field plus QVB, which is charge, velocity times the magnetic field. This velocity in the magnetic component of Lorentz force is velocity of the charge relative to a frame of reference or observer.
Yeah,
In
okay, okay,
Weber's
okay.
electrodynamics, this kind of concept does not appear. Therefore, I call them relational. Also, to distinguish it from Einstein's relativity.
Yes,
Relational is
sure,
not the same as relativity.
actually, let me comment this way. Actually, I find that very feature of independence of coordinate systems, of those very basic aspects, quantities, separation, velocity, and acceleration, very important, and you know, compelling, and so on. So kind of that's I was asking about what came first. But by all means, I think this is very, very important. And maybe later I will ask some questions regarding the transformation of coordinates and then integrability and so on. But here, just
Okay,
one more
I
question.
suggest to those of you who have an interest to give a look at the first appendix,
Yeah, I did.
appendix
Okay,
A of my
Andre,
book,
I did that.
where
I
I
did that.
discuss
Okay, I did
specifically
that.
relational magnitudes.
Yeah, I did that. Actually, that should be visible from my from my question, I guess, in comments. But here,
Okay.
somebody mentioned that guy, that Japanese guy, and then you're mentioning the Lorentz and uh, and stating the preference of gravitation over the electromagnetism. I would actually challenge that and ask if could it be so that in the case of that Newton's bucket, we actually have kind of induction or electromagnetic or say inertial, as maybe Dennis Allen would like to say,
Yes, yes,
induction
yes.
from the bucket to the water. So so that would be the basic, very basic mechanism, and you would have maybe the situation. I would ask you: did anybody check what happens with those molecules of water? Are they rotating in the same direction as the bucket, or has some internal, how say, rotation counter of it?
No, 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 no. In Newton's real experiment,
I'm not talking about Newton. Newton couldn't see molecules. I'm asking you now. Did anybody check that? You know what
oh,
happens?
I don't
What
know. I
is,
don't know. But I
yeah,
know
okay,
that
okay, that will be very important. I would expect.
macroscopic.
Yeah, but okay. Now it's possible. People are looking into the protons. That they kind of separate protons into two vortexes and so on. Here might be actually the situation so that you have kind of counter movement of those structural elements of water with respect to the bucket. So that will be the relational mechanics. How say in terms of how say in the realm of bucket water, in something like then compare with respect to Earth or maybe ether. But if Earth is moving within ether or actually being part of ether, then actually we have everything the same. And the most important thing here would be actually that aspects of relational mechanics that Weber has in his
But
as a
the
result,
only thing I
and we are
can
pushing
say
for.
is that in Newton's real experiment, he did mention that in the beginning, only the bucket did spin relative to the ground. Then, due to friction, the water begins to move with the bucket. At one point, he said in the Principia that he performed the experiment and that at one point, the water and the bucket did perform the revolutions in the same time, so that there was no relative motion between them at
Yeah,
all.
yeah, but if he had
But
looked inside the water in the molecules,
maybe, I don't know. I don't know.
yeah, no, actually, there was suggestion really kind of, these experiments of Samohvalov and what that Dennis Allen is working on and so on. you actually have kind of that kind of induction, that movement of rotational disk actually induces same kind of movement of another disk, coaxial disk. So that movement goes in the opposite direction. Comes like Lenz's law, something like.
I agree, but you see, the essence of Mach's principle is already in this idea. Like let me go back here to the thought experiment by Ernest Mach, which is here in slide 11. So now you begin with the water at rest relative to the ground. And then you rotate thought experiment, Gedanken experiment, okay? Then I have the bucket here at rest. And then I spin relative to the axis of the bucket, like Superman goes there and spins the whole universe, stars and galaxies, once a second around the bucket. Okay? So if Mach's idea is correct, there will be like an induction, because then this will create this curvature in the water. There will be like this effect.
Yeah, okay, but Andre, I mean, I just suggesting to look into that how I say relational effects of the bucket and water. So work with some people, with some fluid dynamics, mechanics guys, or something, to see what's going inside, because there might be some kind of induction and kind of counter movement,
Okay.
a second level. Yeah.
Okay.
Well, I had another experiment, Gedanken experiment. So what happens if you just completely removed all the universe and then you spun your little bucket? What would be the result?
According to relational mechanics, the concavity would essentially disappear. That would remain just a small concavity due to the rotation of the water relative to the ground. But the main effect, according to relational mechanics, is that the concavity depends on rotation relative to the stars and galaxies. So this is a very nice question. If we could annihilate the stars and galaxies, then we essentially would rotate the bucket and the water would not go up, according to relational mechanics.
Well, that seems a very strange result. I see Pal has raised his flag. So Pal, did you want to ask a question? Let's see, we got to unmute you. There you go. Go ahead, Pal. I don't think we can hear you. I think your microphone may have a problem. So why don't you see what you can fix that? It looks like we've got a question from Harry.
Well, Nick and I have the same question. The question is, have you used this theory to calculate the motions of stars in the outer spiral arms of galaxies where the Newtonian gravitational theory fails?
Not yet, but that's an interesting topic. So we might try to apply Weber's law for gravitation in order to study the dynamics of a galaxy, to see, for instance, if the flat rotation curves would come out or not of this theory. So it's an open problem.
In the case of the Newtonian theory, you have to assume that there's this missing mass that is outside of the galaxy that, in your case, I assume creates a kind of a shell outside of the galaxy.
Or maybe the motion of the other stars of the galaxy acting on any test star. So there is relative motion. So, but we need to apply. I don't know the result. It's an open problem.
I would think that would be a test of your theory right there.
Yes,
that's my
of course.
thesis.
Yes.
Well, a difficult problem to solve, I think. Oh, and I have another question, which is, I would think that your theory assumes that the universe is infinite when you're doing these integrations.
Yes, you can do the integration with a finite universe and with an infinite universe. My own point of view, Andre, is that the universe is infinite in extent, in matter content, and in time of duration, eternal. So,
Thank you.
welcome.
All right. Do we have any other questions from the audience today?
Yes, this is Bob Gray. I wanted to ask you, why do you take Weber's force law and electrodynamics and apply that in mechanics, this gravitational force law, without changing the constant c? Should that be like a c prime or some other? Why is it still the velocity of light when you're talking about mechanics?
It doesn't need to be. It's possible to work with a C prime as you wish, and to let this constant open. That's a possibility. I just applied with C because by analogy with Weber original law, but it's just possible to begin with a more general expression. Like in gravitation, we would have C prime instead of C, and then to see if there is any calculations, any effect in which this C prime would appear, and then we could conclude if it is the same as light velocity or it is different. That would be a very nice calculation to do.
Right. Thank you.
Welcome.
So I just had the general comment that this idea that it's the universe outside of us that's controlling all this stuff is highly counterintuitive. Like, and is this all about trying to find an explanation to Newton's bucket? Because I think if you took any high schooler and you showed him Newton's bucket and you asked him what was going on, he would probably just say, oh, well, that's the centrifugal force there, and that's causing the molecules in the bucket to be forced up against the side, and that's why we see that. And if you asked them, if I drop a ball on the Earth and it drops at 9.8 meters per second, and what's that relative to, he would, of course, say the Earth. So I think that's what most people would say. So what is the mystery that causes you to not accept those particular set of answers?
Well, it is the bucket itself, because Newton showed that the parabolic shape of the water is not due to the rotation of the water relative to the Earth. For instance, suppose that I have a bucket here, another short experiment, okay? And I go to an helicopter, okay? And I let the bucket in my helicopter. And in a short experiment, I spin the Earth relative to the axis of the bucket once a second. Okay?
But you can't do that.
No. I can go up in an helicopter, but I cannot spin the Earth once a second. And so this is a Gedanken experiment. But will the water go up? These high schools, maybe they would say yes, if they think that the rotation of the water is relative to the ground. But in Newtonian mechanics, the water will remain flat because the spinning Earth will remain attracting towards its center. It will not exert any lateral force on the bucket. Even when the Earth is rotating below the bucket, it will not exert a lateral force. In Newtonian mechanics, and not according to myself as well, there will be a very small centrifugal force when you spin the Earth, but it would not cause the water to go significantly up in the bucket, just like in Newton's original experiment.
Well, I'm not sure if that's really answering the question, right? The basis of the question is that if you ask any standard trained high schooler, You know, they're not going. They're going to look at Newton's bucket, and they're not going to be mystified. They would be satisfied with the centrifugal force explanation, and that all of this stuff is in fact relative to the Earth, right?
And yes, but they would be wrong. Newton showed that.
Well, I'm not. Well, that may be the basis of my question. How did Newton really show that that was wrong?
Because the Earth only
He
pulls
just explained it
downwards
to
in
you,
his
Franklin.
theory. Well, even when you spin the bucket and the water is moving relative to the ground, in Newtonian mechanics, the Earth only pulls each molecule downwards.
Yeah, but
that comes out of Newtonian theory.
But
Maybe
the
he's wrong, maybe
explanation,
he's right.
the high schooler would say, well, gravity has nothing to do with that. The reason why it's crawling up the side is due to centrifugal force, which you're inducing by spinning the bottle. There's not much of a mystery there. I'm just saying that that's how they would explain it.
But let me give you an a similar experiment, which is very nice. How could Newton, for instance, prove that the Earth spins around its axis once a day? We might say, oh, I see the sun, but when you see the sun, it is the sun which is moving. The sun goes up and then goes down. But it is the motion of the sun, like in the Ptolemaic system, okay? But we can interpret this experiment in two ways. Either the sun and the stars are moving around the stationary Earth, or the stars are stationary and the Earth spins around its axis relative to the stars. So just by this kinematic, visual relative motion, we cannot distinguish who is really spinning. But then Newton was so bright that he said, if the Earth itself spins relative to absolute space, not relative to the stars, the Earth is full of water. So just like in the bucket, when I spin the bucket, the water goes up, okay? So the Earth itself is full of water. So Newton said, if I spin the Earth around its axis, as it's full of water, it should be flattened. So this was Newton's proof, theoretical proof that the Earth spins. Why this was a proof? Because if another Gedanken experiment, if we let the Earth stationary in Newton's absolute space and spins the whole Superman, goes there and spins the whole set of stars and galaxies around the north-south axis of the Earth, the Earth would not be flattened. In Newtonian mechanics, it would remain flat, it would remain spherical. So returning back to your previous question, you said, what would happen if we could annihilate all stars and galaxies around the Earth? That's a very important question, and it was asked exactly in the flattening of the Earth by Carl Neumann, the son of Franz Neumann. He made the following question: what would be the shape of the Earth if we could annihilate all stars around the Earth? The Earth would then be alone in the universe. There is nothing else, only the Earth. So in the first point of view, philosophically, we cannot even talk of its motion, translation, nor its rotation, because there is nothing relative to what it can spin, because it is alone in the universe. So what will be its shape? This is a Gedanken experiment. We don't know.
Okay,
but
the answer too much about Gedanken experiments.
Yes, I know. But this Gedanken experiment is very important, Because let me just finish, please.
Yeah, sure.
Because the answer to this Gedanken experiment is the opposite in Newton and Mach, or in these high schools that you are talking about.
Okay,
Because
you mean in Newton, with Newton, it will be just 1 point, right? Like
no,
source of Big Bang?
the spherical ears, but you annihilate all stars and galaxies. Let me read here
Okay, it will
exactly.
be.
Let me please, let me, this is very important. Just one moment, please. I will read exactly the question by Carl Neumann. This is in my book. Carl Neumann, 1869. What would be the shape of the earth if all other astronomical bodies were annihilated? Not sent away, simply annihilated. This is a Gedanken experiment. But the answer to this question is the opposite in Newton and Mach. In Newton, the earth would remain flat because in Newton, it would remain spinning relative to empty space. So it would remain flat.
By spinning. By spinning, why not just...
No, but just like now. This is the question. I want to discuss this question now, please. So nowadays, we know that the earth is flattened. The amount is very small, is 0.4%. But Newton did calculate that. Let me read the words by Newton in the Principia. The diameter of the earth at the equator is to its diameter from pole to pole as 230 to 229. This was a theoretical calculation. The amount is small. This ratio, 230 to 229, gives 1.004. That is the flattening. I am exaggerating it here in my hand because it is just to show, but the flattening is very small, 0.4%. And it was only 50 years later that people could make measurements, and they did conclude that Newton was right. Okay, so the earth is flattened 0.4%. This is a fact. The distance from North Pole to South Pole is smaller than the distance from the east to west. This is a fact. Newton only made a prediction, but 50 years later, people did make the measurements and confirmed that the Newtonian prediction was right. So now comes once again the question 200 years later by Carl Neumann. What would be the shape of the earth if all other astronomical bodies were annihilated? So would the earth remain flat, 0.4%, or would it become spherical? This is a very clear question. The earth is alone in the universe. Does it make sense to you that it spins? Does it make sense to you that it spins once a day relative to what?
No,
Does it make
no,
sense to you that it will be flattened?
Are you
So
asking us what to tell us?
Just finish, please. In Newtonian mechanics, it will remain with the same amount of flatness, 0.4%. According to Ernest MA, it would be spherical, because it is alone in the universe. It does not make sense to talk about the spin of the earth. Therefore, it cannot happen any dynamical effect. And I agree with Mach. And, and moreover, in relational mechanics, we show that the amount of flattening of the earth is a function of the mean matter density in the universe.
Okay, look, if you will be experimenting with that, with the bucket.
When we make this mean matter density goes to zero, the earth, which was flattened, becomes spherical.
Can you guys hear me? Can you guys hear?
Yeah, Neil.
It's an interesting proof that the universe is made out of something. Implication is the universe is made out of something, and therefore, even though you take all the other material away, the universe is made out of something. It has a north and a south, and the Earth is relative to the universe. That would be an interesting proof that the universe is made of something. If the universe is made of nothing, then of course you wouldn't have a flattened Earth.
Yes. So this is.
May I tell you something, guys? Just a moment, yeah. Just a moment. Somehow to get back to that kind of F equals ME A and the Newton's formula of gravity, that where force depends on masses. On the other hand, acceleration doesn't not. I think that actually Newton was working with that bucket in order to, how say, prevent critics related to his force of gravity, where inertial and gravitational force are equated, and then to avoid critics of the fact that when you apply F equal ma to the case of one mass with respect to the Earth and the other different mass, where F equal ma is kind of supporting that formula. If you turn around and look how Earth is being accelerated toward those two bodies, one or the other of different mass, then F equal ma would not work. So I guess Newton's bigger concern was about that, and he was considering that bucket that could be really kind of a local relational mechanics dynamics related to count related to the ether, which I could support very well. But basically, he was wanting to how say to prevent critics on that part, a very basic part of flowness of his very law of gravity and relevance of mass into that in those processes of gravitation and orbital motion. That's why we have that postulation of dark matter and so on and so on. So actually, instead of looking into those kind of Gedanken experiments too much, we just may want to get back really to those very initial problems and how they were kind of overcome, and how other problems came into play to support or somehow to hide those very basic weaknesses.
Okay, looks like we've got a question from Harry Ricker. And if you guys have a question, you guys can try and break into the conversation, or you can put up the flags. But go ahead. You there, Harry?
I guess I should apologize. I forgot to take that down.
Well, then Cornelius has a question.
If you want.
Well, then go ahead. This is your time.
Well, let Cornelius go.
Okay. Cornelius, are you there?
Yes, I'm here. Okay.
Go ahead.
Yeah, in accordance or thinking, going back to the thought experiment, basically what would happen with the Earth if the entire universe were removed. Basically, with Mach's principle, since the mass of the Earth is relative or is related to the motion of the universe, if the entire universe was removed, the mass of the Earth would have to be removed also, because it is basically an integrated part of the universe. You can't have the Earth without the rest of the universe there.
Really? Why not?
Because they're an integrated part. They're all part of one field that has to be focused to become an Earth. That's
I don't necessarily see that.
That's why Mach's principle makes sense, because if you're moving the Earth, you're actually just moving a pattern of waves within the field, and the waves are continuous throughout. Matter has been shown to be not a focused, isolated point, but have no definitive edge. And the same is true of the Earth. It's all part of the matter. So essentially, that's why Mach's principle makes sense, because you're actually moving wave patterns within wave patterns.
So your main point is that you couldn't perform the Gedanken experiment, even in your mind.
That's correct. You couldn't have an Earth without the remainder of the universe. They're all one integrated part.
Well, I'm going to play the devil's advocate and say, well, that seems like a lot of hooey.
Okay.
Because
That's a pretty good argument. That's a really
yeah,
good argument.
I know. Isn't that the good argument?
Yeah, Huey is a pretty good scientific term.
He is.
Okay. Anyway, that's my input to it.
But just as a skeptic to the whole Mach's principle thing, that it seems hard to believe that that when I drop my calculator here on my desk, that has anything to do with some galaxy far, far away.
Well, you're just not moving it. You're just not moving your calculator near the speed of light.
I mean, how many people here actually believe in Mach's principle? So I'll put in my vote to say I don't believe it at all. So I'm just curious: are there anybody else who thinks that this Mach's principle is not right? Just kind of take a poll here.
Well, raise your flag if you believe in Mach's principle.
I don't know how to, I don't know how to raise a flag, but I believe. I defend it with all my heart.
Right-hand corner, there are 3 dots, and it says menu, and you open the menu, and there's a raise your flag in the menu.
Okay, I raise my hand.
Yeah. Although
I'm totally in favor of Mach's principle.
Okay.
I'm only showing one flag at a time, so it's kind of hard to take a poll. So I can see like Liv Tickner raised his flag. And
I'm simply giving a definition of why Mach's principle can work in my view.
Because it seems to me that this is all basically denying, or you have to explain where centrifugal force comes from. If you can explain centrifugal force,
this is the essence, frankly. This is the essence.
But if you can explain centrifugal force as a local effect, then you don't need to invoke the rest of the universe to explain it.
It only appears as local effect when you're running it at very low speeds.
But Franklin, what would be a local effect? How far out do you have to go, before it's not a local effect anymore? Do you go the solar system, the galaxy?
As an etherist,
as far out as we can see, how far is that?
As an etherist, I would say you only need to go as far as the local ether field. So
well, that's why ether is a desirable idea.
Yes, because in order to explain the centrifugal effect as an etherist, we would just say that effect is happening relative to the local ether field, and it has nothing to do with far-flung galaxies.
Yeah, that's why ether is a really nice assumption.
So
you have no mechanism for the origin of mass. You just believe mass exists.
Yeah, everything. Literally, yes, I would agree with this. Frankly, it account the ether, and then that would be something like what can make what can be similar to or can replace Mach's principle. How to say?
Yeah, I mean, you could balance it and say, well, you have Mach's principle, and all of these effects are relative to that, or you could say all of these effects are relative to your local ether. So if you have a particle and it is rotating relative to your local ether, that's how you explain the
local might be kind of relative. Local can be really local, can be extended, more extended toward really kind of really kind of universal or maybe what Newton had in mind. You know what I mean? So there are different levels, different scales, where we have always either in motion of larger or smaller extent, and so on and so on. If we would somehow try to kind of think of some substrate which has kind of such a feature, so that whenever you have kind of homogeneity and how say isotropic movement, then there will be something like absolute referent frame. That would be then kind of Newtonian space. And then Mach comes something like less considering things maybe in smaller domain. Again, big, large, ultra large domain. But going that way down to the Earth, then we can move consider the movement of ether of Earth as being is part of ether which moves together with it, actually, which is part of ether of Earth itself. So one has to have in mind actually that scaling, the sizes, the levels, how to say, of reality with ether as a basis.
At what point in space does the Earth's magnetic field or the Earth's gravitational field discontinue or no longer exist?
There is no end of it.
There you go.
Exactly.
You mean
That's because it's tied in with the rest of the universe.
But it
gravitational field.
Diminishes to a level that is no longer noticeable.
That's correct, and
wait,
that's why the rest of the universe doesn't have much of an effect on the Newton's bucket, because it's most strongly affected by the local strength of gravity.
The shell at a distance, in fact, creates a field that is flat in the neighborhood of the Earth, and the Earth does then deform that field. And so you need field equations to comprehend the whole thing.
Don't we all agree that
Maxwell
if there
equations
were,
are a kind of field equations.
guys, do we all agree that if all the matter material in the universe disappeared except for two, that eventually they would be drawn together?
Yes, sure, definitely. We
Okay,
will push.
so
Then we will be pushed to each
Then
other.
there's no end to that field.
No, there is a kind of Pauli principle that prevents that.
But
Huh?
I would say the way that you're using the terminology is a little concerning, because
Can't hear you.
I thought Newton and Weber, etc., were not field theories.
Yes, they were not.
Correct. Which leads me to my question that I'd like to ask, if I could.
Okay.
In your book, do you address, you said earlier, and you sort of passed over this, you said that Weber's law could explain Faraday's law. And my
Yes.
question is, can it explain the superconductivity effect that sort of would appear to violate Faraday's law because there's no motion, but yet there's a reaction force?
Which example, please? More specific.
In the case of a superconductor, you can suspend a magnet over a superconducting surface, and the magnet will stay there suspended when it's not moving.
Yes.
And so that would mean that Faraday's law doesn't apply because there's no motion of the magnetic or change in the magnetic field, and yet there's a force that suspends the magnet. And
yes, and this force is Ampere's force. That is Ampere's force.
Please don't argue with me. I'm wait a minute. I'm sorry.
Go ahead,
I
Harry.
didn't hear anything.
The force is Ampere's force, which holds the magnet or the circuit above the magnet. That is Ampere's force.
So you're assuming that there are electrons moving around in both the magnet and in the metal.
Yes.
Okay. So you think your theory does explain that?
Yes, of course.
And so, okay. All right. So I guess my next question would be...
That's not my theory. That's the theory from Wilhelm Weber.
Well, you made the statement that it had been verified. I'm assuming by you.
Okay.
All right. Well, basically, my question is, Weber's theory isn't a field theory. So my question is, why do you think people are not paying more attention to Weber's theory as opposed to the Maxwellian field theory?
Well, I believe this is a very complex question because it has to do with history of science, sociology, many aspects, but it has been completely forgotten. People, they don't know any longer about Weber. They don't learn it in the textbooks. Even Ampere's force between current elements is no longer taught in the textbook. So no one knows about it. Even what we call Ampere's circuital law is not due to Ampere himself, because he never spoke of a magnetic field. What he really did was an expression for, let me show it here again. This is slide 15. What Ampere obtained, his main result is not based on magnetic field. It's not circuital law. It is a force law between two current elements, which falls as 1 over r square, which is central and which is proportional to the current 1 and current 2. So this expression was called by Maxwell the most important formula of electrodynamics. In Maxwell's treatise, you can read it, but it was disappeared from the textbooks. So
But
no one knows any longer about Ampere.
Let me just ask this question.
All these three laws.
Let me ask this question, if I might. My perception is that the Hertz, when he demonstrated radio waves, that pretty much was what caused people to move away from Weber's theory. Would you agree with that?
Not exactly, but that had an influence, because Hertz was working under Helmholtz, and Helmholtz was the main enemy, if we can call it, of Weber.
Yeah, right.
So Helmholtz had a huge effect in making Weber theory disappear, and Hertz was his student. So that had an influence.
It may be because there are too many thought experiments and not enough experiments that actually work and you can observe these things. There's an awful lot of this seems to be based on thought experiments. The one thing that throws me, for example, is that
I would say the opposite, because Weber was essentially an excellent experimentalist.
Okay, well, you were talking about the sphere with the water inside of it, and it just seems to me that if you have the core of that rotating sphere, you're going to have different forces on the water than you're going to have on the outer edge. And you can imagine when that question was raised about molecules, what happens with the molecules in there, there's probably little bits of orbiting and molecules moving to the outside, moving to the inside. There's lots of stuff that goes on inside of there, and it doesn't sound like that's taken into account, because the sphere presumably is a solid and the water is a liquid, and things happen different in a liquid than happen in a solid. So I can imagine spirals and things moving toward the outside, and yes, those spirals would imply the molecules are actually not only going forward and backwards, but also laterally. And then you can kind of imagine, well, a solar system like a movement going on inside the water where you have these little spirals going in and out. Well, that's an experiment that has now become too complicated to even contemplate. Just saying.
These three equations that are put here can be derived from field theory. So I think field theory is more deeper than these three equations.
Maybe they are. I don't think so. I don't agree. I am totally in favor of Weber's electrodynamics, and I'm trying my best to revive it.
I can show it to you, but not here.
Okay, send me that later on.
I'll do.
Thanks.
In the professor's book, you can see how from Weber's theory, you can derive the Maxwell's equations under certain conditions, which is the field theory. So you could go either way. You can then reverse all those derivations and go from the Maxwell's equations and the field theory and go under certain conditions, go back to the Weber theory.
Under certain conditions, maybe. Right. And I call your attention once again, please try to read Maxwell. and read and see the last chapter of volume 2 of his treatise. And there he shows that from Weber, you deduce Ampere's circuital law, Faraday's law of induction, conservation of energy, and he says that it's very important that two completely different theories, one based on field theory and the other, like Weber, based on direct interaction, both yield the same experimental results. Try to read Maxwell. Don't believe my words. Read Maxwell.
Well, going back to the question of experiments, you said that, certainly this is something which could be realized. I mean, you might have to build a really big and expensive experiment, but what experiments have been done, and have they just truly produced no results so far?
Nowadays, no one knows any longer about Weber, nor about Ampere they know. So there are many experiments in the last maybe 40 years, for instance, performed by father and son, Peter and Neil Granot, trying to distinguish Ampere's force from Grassmann's force. So there is a going on discussion on this topic, but these are real experiments which have been performed in the last few years. There is still a discussion about the interpretation of these experiments, like exploding wire, mercury fountain, electromagnetic impulse pendulum, many different experiments performed in the laboratory, in the USA, in Oxford. These are real, not thought experiments, papers published in Nature, Physical Review, etc. Just give a look at these books by Peter and Neil Granot.
I mean, I would think that that experiment you proposed, where you you measure the force of gravity inside of a shell, it could be easily realized. I mean, we have very, very sensitive gravity meters. I could easily see you building a gigantic concrete shell, and you could put that gravity meter inside and outside.
Order of magnitude is that we can measure is 1 part in 10 to 10. But the gravitational effect we are talking here is 1 part in 10 to 24. So we cannot detect that.
Maybe you can. I don't know. I mean, these gravity meters are super sensitive. So,
maybe. Who knows?
But it's just something to look into. I mean, you could sit there and stick it inside of, I don't know, like a dome stadium or something. You could use that as your mass, which would be millions and millions of tons. And with a super duper sensitive gravity meter, could possibly pick up a difference that small.
Maybe.
But that would be something that's convincing. I mean, for a skeptic like me, if you could show that there's some difference there, then that might be convincing. Otherwise, it's kind of your word against mine kind of thing.
Yes, I know.
I think the best
but frankly, if you have the opportunity, I don't know if you have already, try to read these papers and books by Peter and Neil Granot, just for a beginning, for a start.
Can you put a reference to those in the chat? Just do you know how to use the chat box?
Okay, let me see.
I think that if you click on the, let me see here. There's a little blue. Well, there's on the bottom. There's a little thing that looks like a chat bubble or something. I think you click that, and that brings up the chat.
Peter, let me write it down here.
Yeah, if you can write it down in the chat, then we can have that. And I can transcribe that to the notes.
Can you read Peter and Neil Granot?
Peter and Neil Granot. Yeah, okay. I can transcribe that to the notes so people can can look that up for themselves.
Yes. Most people have read it.
Always...
I've read the book.
Do you know what the name of the book is?
Oh, there are many. For instance, Newtonian Electrodynamics is one. Let me write it down.
Newton versus Einstein is another. In the Grip of the Distant Universe is another.
I'm writing another one.
I can see this is going to be a big project.
Okay, just two here on electrodynamics. One is Newtonian electrodynamics, and the second is the Ampere-Neumann electrodynamics of metals. many different experiments, real experiments, trying to distinguish Ampere's force law from the Biot-Savart or Grassmann force law. Very interesting.
Yeah.
Modern.
I guess there is a longitudinal force, right? Between two conductors with wire, right?
Sorry, I didn't understand.
So I guess that you had chance to work with, maybe derive the force, or maybe Weber did it for the force between two conductors which are aligned on the same line. So that so-called longitudinal force.
Yes, this is one
No
kind of
zero,
experiment, the
or,
exploding wire
yeah,
phenomena.
non-zero magnetic vector potential divergence and so on. May I ask you one question regarding I announced that question regarding general applicability of relational dynamics for integration of systems without reliance on the Christoffel symbols.
Okay.
Did you work? I mean, I saw in your book that chapter, that annex, right?
Yes.
Exposing those features of I say invariance, but maybe contravariance or whatever. When it comes to integration of the dynamical systems in different coordinate systems, is there need to rely on to keep track of Christoffel symbols all the time?
No,
One can do it.
not at all.
do- uh,
All these questions of Christopher's symbols, transformation, Lorentz transformation, and so on, they arise for expressions which depend on the velocity of the test body relative to an observer. In relational mechanics and in Weber's electrodynamics, these problems, they don't come out, they don't appear, because
when it comes
only relative magnitudes are relevant for the force.
when you do integration, for example, to get some particular orbit or whatever trajectory of particle,
Yes.
you can do it just kind of how say without resorting to those. There is one
Because you work in the frame of reference of the distant galaxies, which I call universal frame of reference.
Yeah. I may
Then
send you. Look,
the
I may
motion
send,
relative to this frame.
I may send you some works of certain professor here, pretty aged guy in
Yes,
Belgrade,
I would like to give a look.
who is pushing for
Okay.
something like that, and I have been seeing similarities. So I wanted to consult you about that, if possible.
Okay.
Okay, thank you.
Okay, so we're getting towards the top of the hour here. So what I'm going to do is I'm going to I've been listening the whole time. I'm just going to try and summarize a little bit about what this meeting's have been about. And you can correct me if I'm wrong. And then I'll let Dr. Cease close, okay? So, but we've been talking about this theory of relational mechanics. And it started out with a discussion of, according to Newton, what's this gravity force 9.8 meters per second relative to? And I believe he said Newton thinks that this is relative to empty space, not relative to the Earth. And so he also tried to show that with the rotating bucket, and that that as the water matches the speed of the bucket, that he's saying that there's this empty space frame. So, but that was different from what Mach was saying. I think Mach was saying that it was actually the heavens that was the frame of interest, and that there would be different effects if like the entire heavens rotated versus what Newton was saying, that there's this empty space frame. Then we got into Weber's electrodynamics, which is unifying these various equations of Ampere's law and Coulombs force, and I couldn't quite really understand what all that math was, but the bottom line seemed to be that the constant G, in fact, relied on things which were out in the universe. Is what it seemed to be the main bottom line here. So this whole force of G is actually coming from outside the Earth and not really inside the Earth, it would seem. So, and that this acceleration, 9.8 meters per second, is actually relative to the spherical shell of galaxies around us. But this does make specific experimental predictions. There were 2 experiments cited, and that we should see a difference in the acceleration rate. However, those differences are so small, we've not really been able to detect them yet. And like most experiments, probably cost lots of money to do. But maybe you can get an experimentalist interested in it. They're always looking for something to write a grant on. So, but that seems to be the general, at least what I got from it. So I'm going to let Professor Assis close and see whether I got any of that right. So go ahead.
Yes, it was a great summary. Thanks very much, Franklin. And I thanks also David Hilster once more for this kind invitation. And if you wish, I can come another day and discuss other subjects if you wish. Thank you very much, all of you, for your patience and attention. Thanks.
Well, you're always welcome here. We're always here. I'm going to be trying to do this every week, same time, same place. So I thank you. This is one of our first presentation type chats. But normally we always just get together and I just sort of stir the pot and we talk about anything that's on our mind. All right, so you're always welcome to come back, but that will do it for this week's conference. And if anyone else would like to present anything, like Professor Assis, I would invite you to send me a message and we would be happy to have you. So if you have any new papers that you want to discuss, bring them on. All right, so signing off for